Okay, so focus 5 is all about mixtures and the thermodynamics and quantifying what drives a certain type of mixture. And pretty soon we're going to have to start taking into account chemical character, which makes mixing more challenging than one would think. But starting with something simple, okay, I have a glorious blue liquid. That's creepy. So this is ink. Just took my pen and threw some ink in water. So this is, we've got two mixtures, or if we've got two solutions. The idea is if you pour, that went kind of fast. If you pour the two together, what drives the mixture of this water and then the blue ink? And I can do it again, slow-mo. There we go. You can see some of it. So the question is, what drives that mixture or drives that mixing? And if I were even better, I could. There we go. It's more of a direct mixing. It's the worst time to wear this sweatshirt. So you've got multiple things going on here. This is a water-based ink. So these ink molecules are being carried by the water. So you've got a solution of water and the ink. And the mixing of this is an entropically driven mixing process. If, however, this was like an oil-based ink, it would be, there would be additional aspects to the mixing or the driving force behind this mixture. So now I'm going to add some work energy into getting this mixture to go. And I mean, you can see there's still little vortices and such. But quantifying the thermodynamics of the mixing is pretty challenging because we have to now incorporate how the system properties change as we change the number of particles present. I have ink everywhere. Okay, so if we had been in groups or in class, I would have done a different example, but that's all I have with what I've got around me. So that's what we're going to do. So I'd like you to think about ink mixing together in water. So here we go. Simple mixtures. A mixed with B. Or I should say, this chemical reaction of A going into B. Okay, so if you have times 0, you've got a bunch of A's, and then you've got T equals some later time, and you've got A becoming B, and then finally you've got pure B. Okay, so this is the goal, is to get to where we can quantify chemical reactions where A turns into B. But there's really no difference between really just mixing A and B together until you've just got pure B. And so that's kind of the approach that we're going to take, is pretending that this is the same as just mixing the two products together, instead of actually having the reaction create the products. Okay, so how do we quantify these so far? All right, so we've got delta G equals the work energy. Delta H equals the heat energy. And delta S is equal to the entropy. All right, so delta G equals delta H minus T delta S. By the way, this is of the system, not total. So if, say, you have an exam that you're trying to correct, and all of you are like, oh yeah, this is what defines spontaneity. That's of the system, not the total. Okay. What do I want to say? Okay. So we want to relate the thermodynamic potentials and entropy, so the thermodynamic properties, to this process, which means we have to now relate the thermodynamic potentials to, so we need to relate them to the quantity of A and B. That's a problem, which means we need to relate it to the number of moles of A and the number of moles of B. And that's where we haven't done that yet. So how do we do it? Okay, I decided I was going to actually kind of show you the demonstration that we would do in class via drawing it on the board. So we have volume as a function of temperature, pressure, and the number of moles present of a mixture. But the problem is these are no longer linear. 18 milliliters of water, I have a beaker. I have two volumetric flasks, what are those things called? Graduated cylinders of 150 milliliters of ethanol and 150 milliliters of water. I'm going to pour 18 milliliters of water and 18 milliliters of water into both of my graduated cylinders. And again, imagine me putzing around trying to do this in class. And then I'll have y'all look and measure, okay, well, how much has the volume increased? Let's start with water. If I add 108 or 150 milliliters to 18 mils, if I add these two together, water and water, what will be the volume? 168 milliliters, which is 150 plus 18 milliliters. Cool? Linear. Any guesses what the volume would be if I add 18 milliliters of water to 150 milliliters of ethanol? $164 milliliters. The volume is not additive because the values or the identity of the solvent or solute and solvent are different. So you actually get 164 milliliters. So this is due to the differences in the hydrogen bonding that cause a variation in the expansion or contraction upon the mixing. What that does is it makes this only true if your system is pure, a one component system, which means now we need a function to describe how the volume is going to change if we add a new component. So now this becomes a function. Go team. Okay. I also dress up this demo. You have no idea what the values are. You think I'm just adding water. Chemistry rule number 1, never assume clear liquid is water. Okay. So we have we know we have a function. We just don't know what it is. So this is for a 2-component system. So what do we do? Well, let's start with the total differential. dV is equal to how the volume changes when the temperature changes with pressure N1 and N2 constant multiplied by the actual change in temperature, plus how the volume changes when I change pressure at T constant, N1 and N2 constant multiplied by the actual change in the pressure, plus how the volume changes when I change the number of the moles of the first component with temperature, pressure, and the number of moles of the second component constant multiplied by the actual change in the number of moles of the first component plus partial V, partial N2 with T, P, and N1 constant multiplied by the actual change of the number of moles of N2. Okay, so we are going to define a new quantity. V bar is equal to how the volume changes when I change the number of moles at constant N2, T, and P. This is called the partial molar volume and is a new quantity we will use to describe our systems. Molar volume of component 1. Okay. Such that, okay, go team. Write that down. I'm going to erase and make more room. Okay, so at constant temperature and pressure, those first 2 terms went to 0 because dP and dt are constant or 0. And so I've got dV is equal to partial V partial N1, partial V partial N2. I'm going to call this V1 bar and this V2 bar. This bar here indicates that it's a partial molar volume. Atkins encourages that you use the bar. Sometimes you just use V1. The bar is nice because then it says, hey, this is a partial molar quantity. So this then becomes V1 bar dN1 plus V2 bar dN2. Don't think that's a volume. That's a partial molar volume. Very different. dV, integrate, integrate, integrate. Then this tells you that we get V is equal to V1 N1 plus V2 N2. If you integrate from 0 to N1, 0 to N2, and 0 to V. Cool? Oops, 0 to V, not integrate this part. Okay, so this looks like a partial pressure. Awesome. So the total volume is equal to the partial molar volume times the number of moles that you have of the first component plus the partial molar volume of the second component times the number of moles of the second component that you have. Woohoo! If you were to plot this, let's say you plot this as a function of N1, it might look weird. It might look something like that, say, to where you have, this is your actual volume. You'd have to go into the lab and measure this, but then let's say this is water and ethanol. Oh my God, I can't spell. ethanol. There we go. So let's say this is water and ethanol. Okay, I just looked up what that plot would look like. It's figure 5A.1. And if this is water, it looks something like this. So where this is the volume of water, and then as a function of ethanol. So there's like this little uptick and then it goes down. So you get to a point where you're adding the majority of ethanol and the partial molar volume is decreasing, which means dV dN is less than 0. Well, that says that as you increase this, the volume goes down. So you have a contraction. And it's not that the volume is reducing, like you're getting a negative volume. It's that as you add, like, and you saw this earlier in the example, as you add 18 milliliters, the final volume is 14 milliliters different. And so that's causing a smaller final volume than what you added. Okay, so partial molar volumes can be negative. That's kind of strange, but this is a nonlinear relationship. So it's no longer this idea that if I add, from my earlier example, 2 amounts of, say, clear liquid and blue liquid, that I get a result of equal additive linear combinations. Cool? Okay, next thing. Okay, I have no idea how much I've just got shown. Okay, so the chemical potential. So the definition of the chemical potential is how you have the chemical potential is defined as the partial molar Gibbs energy. How much the Gibbs energy changes when you change one of the components at constant T, P, and all the other components held constant. Cool? Okay, so we have dG is equal to V dP minus S dt for a one-component system, but we also have plus mu A dNA plus mu B dNB, where this originates from having multiple components. If you have just a one-component system, all of this goes away because dN is 0. There's no change in the number of components present. So this is actually the complete fundamental equation of thermodynamics that incorporates the changing number of moles. And so under constant pressure and temperature conditions, the change in the Gibbs becomes the chemical potential, representing, just like the partial molar volume, the change in the Gibbs with respect to how the number of moles of A changes. So this is the chemical potential or the capability of the Gibbs changing with respect to the change of the number of moles of one of the components. Cool. So this equals the work of non-expansion. And before, you probably had some challenges in grasping non-expansion work. And I kept saying, crap, I have to sneeze. So sorry. Oh, goodness. Ugh. Pause. I'm going to cut that one out. Okay. So before, you had problems, or maybe had problems in grasping what is non-expansion work. Gosh, I have to sneeze again. I'm so sorry. Ugh. Okay. Before, you had problems in grasping, maybe you had problems grasping non-expansion work for the Gibbs energy. This comes from this idea that you've got chemical work coming from the change in the number of moles present. And that's chemical reactions that are occurring. There's work that can be done that isn't based on just a one component system doing something like expanding, contracting, punching something, whatever. Okay. Change in the number of moles changes how much work energy you can get out of your system. That's what this says. All right. Cool. That's all I got, actually. The power of the chemical potential. Yay.